Okay, good evening. This is Dr. Jensen, and we're going to start off with our atomic masses. So we've been looking at the periodic table, and in our previous lecture, we looked at the different kinds of elements, whether we're looking at metals, metalloids, and nonmetals. We understood that there are families of various elements, that they have different physical and chemical properties that they are grouped by. And we also looked at the isotope designation, which looks at how many protons a particular element has. In an isotope, how many neutrons it has. It makes it different. But on the periodic table, there are a set of numbers that you will find on any periodic table. And this is the atomic mass. Okay, so the atomic mass is different than the mass number. Okay, because each one of those elements has a variety of isotopes. And so on the periodic table, you will find an average, the weighted average of the different isotopes. Okay, so as we talked about before, in the basic numerical value for the proton, we looked at atomic mass. The proton weighed 1 atomic mass, that a neutron weighed 1 atomic mass. But the atomic mass unit as a unit is not, or AMU as we call it, is not really a functional unit. It doesn't help us to do anything. So we have to try and put some units, a real world unit, onto those numbers that we see on the periodic table. Okay, so again, the numbers that you see on the periodic table, commonly there is a single kind of bold number that indicates how many protons the number has. And then the second number is the atomic mass, okay? Which the atomic mass is, it's similar in the name to the mass number that we talked about from the isotope designation, but it is not the same thing. Okay, the mass number and atomic mass, again, they both have mass in it, but they don't mean the same thing. Okay, so the atomic mass that we find on the periodic table is the weighted average of the naturally occurring isotopes. Okay, so each isotope found in nature is relatively constant. Okay, so the percent abundance of each one of those isotopes naturally found is then weighted times the mass of that isotope, okay, in order to get the atomic mass that you find on the periodic table. Okay, so this is why you see decimal place weights, right? So we talked about before that, when we have, if you are weighing out, the number of protons and the number of neutrons, that the mass should just be those two things, right? And if they're roughly 1 AMU and 1 AMU, then, it means like hydrogen would be 2 AMU, or 1 AMU, and then helium would be like 2 AMU, and so on. And so but we find that the masses are more than that, or that there's fractional values in there, decimal places. So there is some weighted value that really ends up being, okay? So we want to put an actual unit to the number that we see on the periodic table, okay? And so to do that, what was done was to use a standard value. Now, at different times, chemists argued about what should be the standard value. Eventually, it came down to that we should use carbon as our standard value. And so the number of atoms, okay, if we had to gather up enough atoms of carbon, okay, that it has a roughly the mass of 12 AMU, although the unit is grams. So the question is, how many atoms of carbon would you need to make 12 grams of carbon? And so the answer is 6.02 times 10 to the 23rd atoms of carbon. You would get exactly 12 grams of carbon. So this is called Avogadro's number, and this is the definition of what a mole is. So the mole is just like a dozen pennies, okay? If I talk about I have a dozen pennies, you know how many pennies I'm talking about. I always have 12 pennies. If I have a dozen eggs, you know how many eggs I have. If I have a dozen cars, I have 12 cars. So if I have a mole is just like, a mole is always defined as 6.02 times 10 to the 23rd. So if I have a mole of pennies, I have 6.02 times 10 to the 23rd pennies. If I have a mole of feathers, I have 6.02 times 10 to the 23rd feathers. Okay, so it is the same thing as like a dozen. It's just a much bigger number because we're talking about atoms. How many atoms do we need to gather together in order to have a substantial mass in order to weigh? Okay, so now when we look at the periodic table, so if you open a book and you look at the number for lithium, okay, you'll see this number 6.941 on the periodic table. All right, let me see if I have one of my earlier periodic tables that has the numbers on it. Okay, it's a little hard to read, here, but you can see this is a common way that you see the periodic table. So you'll see here the way the periodic table is set up. So there will be things like oxidation states or the common charges. The atomic number right there. There's, as I said, there's usually a big bold number that goes with it that tells how many protons does the element have. Okay, and then here the standard atomic weight is this value here. So usually you will see the standard atomic weight, and so over here 6.94 is the atomic weight for lithium. Okay, now before now we would have said that was 6.94 AMU, or for the iron here that it's 55.845 AMU. Okay, but we're gonna skip over even really putting AMU as a term, and we're gonna call these grams per mole. Okay, if you gather, so if we look over here at carbon, here's what I was talking about, 12.01, okay, that is the weighted average of its isotopes. Okay, so it commonly has 6 protons, it commonly also has 6 neutrons, which puts its AMU at about 12, okay, but it's slightly more than that, which indicates that there is some percentage that is carbon 13 that has 7 neutrons and 6 protons, and so the average value gives you the 12.01, right? And so this value indicates that if we had a mole, 6.02 times 10 to the 23rd atoms of carbon, it would weigh 12.01 grams. Okay, so now everything now, all these numbers now on the periodic table now have the units of grams per mole. Okay, if we get a mole of them, 6.02 times 10 to the 23rd, they will now weigh this many grams. Okay, so iron will weigh 55.845 grams per mole. Okay. So oftentimes the atomic mass or molar mass, the way that you will hear me talk about this is called molecular weight, right? It's obviously not a molecule, right? So silver is not a molecule of silver, it's an atom. So you might say it is the atomic mass, right? Or they will say the molar mass or the molecular weight. So those are 3 ways of talking about the same thing. Okay, they're just synonyms referring to the same value. Okay. So when we look at it in element, okay, so this is the molecule benzene, right? Benzene is C6H6. So the element has its designation, carbon. Okay. The subscript tells how many of the previous tells how many of the carbons there are. So the 6 here is talking about how many carbons. Hydrogen, there are 6 hydrogens. So the 6 is talking about how many hydrogens there are. Okay. In the water, okay, there is hydrogen. So there are 2 hydrogens and 1 oxygen. Okay. So if we wanted to know what is the molecular weight of benzene, okay, you are always going to have the periodic table available. You don't have to memorize molecular weights. Okay, we talked about this last time. We don't have to memorize molecular weights. So if you have the periodic table available to you, you know what the molecular weight is for carbon. You know what the molecular weight is for hydrogen. You just need to add them together to get the molecular weight for the whole compound. So we just have to multiply, in this case, carbon's molecular weight times the fact there are 6 of them. We have to multiply hydrogen's molecular weight times the fact that there are 6 of them, and then add those together, and you will have the total molecular weight for the molecule benzene. Okay. Now, the questions usually come for how many digits off the periodic table should I use? For most questions, when you're doing this, 1 decimal place is usually sufficient. Okay. If we're really trying to be accurate, you can use more digits, but especially if you're looking at a quiz question or test question, the answers are not significantly similar enough that the sig figs are going to make a difference. Okay. So if we look at an example here for what we're going to call aluminum oxide, right? Aluminum, there are 2 aluminums and there are 3 oxygens. So when we're doing the molecular weight, this value here, 26.981, comes from the periodic table. Okay, if you open up your book or look at a periodic table that you have, you will find this value on there. Okay, oxygen, most people will shorthand just say 16. Okay, is multiplied by how many of them there are. Okay, how many are in the molecule. Okay, so this is where I was saying last time that the nomenclature is not necessarily, I'm not asking about the molecule on the test, but if I gave you a molecule, I said that there were, what is the molecular weight for aluminum oxide? But I didn't give you the formula, okay? You would have to put the formula together in order to calculate the molecular weight, right? Because you have to know how many aluminums am I putting together? How many aluminums are present in the molecule? How many oxygens are present in the molecule? So 2 times our 26 and 3 times 16 gives us the weights of the individual elements and then adding them together. So the total molecular weight for aluminum oxide is 101.9. Okay. Here's a little more complex molecule. Now, obviously, these get more complex as we look at a variety of these kinds of problems. Right? The carbon, again, the 12.01 grams per mole for the carbon is multiplied by 13 because of the subscript. Okay, so in this kind of case, you would have to know, what the formula is. Okay, now for organic molecules, we're not really going to get to organic molecules, right? But you'll have the formula in this case. So there are 13 carbons, there are 10 hydrogens, and there is 1 oxygen. Each one of the values in the parentheses is something you would have already. You would have a periodic table, so you would have these numbers. Okay, so here I'm just multiplying them individually and then adding them all up afterwards. And so this gets us to the grams per mole total molecular weight. 182. Okay, now before I get too far, don't forget the poll everywhere. You may want to pull up your poll everywhere. There is a poll that will come up. I don't know if it's next. Okay. All right. Another example. All right. So here we see an example here for aluminum nitrate. All right. The aluminum, 26 grams per mole, right? So here you'll see double parentheses. Now, the reason why we use the parentheses is because the NO3 here is one molecule, okay? It's one molecule, it's a chunk of stuff. And so there are 3 of everything in here, all right? So in this case, it's 3 times 3 for the oxygen times 3 for the nitrogen. And I don't know where my slide that, oh, okay, there it is. All right, so the question is then, how many so there are a total of now 9 oxygens that we have to account for, right? And there are 3 nitrogens we have to account for. Okay, so it's 3 times everything in the parentheses. Okay, so the molecular weight for aluminum off the periodic table times how many there's no subscript for 1, so it's just, if it's written in there, there is 1 there. It's 3 times everything in the parentheses. If you don't use the parentheses, then it looks like you got 33 oxygens here. And you'll see this again when we get to the nomenclature stuff as well. Okay, and we sum up all of that and we get 212 grams per mole. Okay, so as I said, so this is what you commonly will see from a standard periodic table. That first one had a lot of extra information in there. This one has what your standard periodic table would give you. For carbon, you get the mass number. How many, or the atomic number is how many protons does it have? And then you get the atomic mass, 12.01 grams per mole. Okay. So you always have the periodic table. Okay, so you should be able to add weights together for any molecule. Just the difficulty will be if I don't give you the formula and you have to employ some of the nomenclature to get to the formula. Okay. All right. So it looks like somebody's already, I think it was already active here. So what is the molecular weight? This molecule is called calcium sulfate. What do we think the molecular weight is for calcium sulfate?
We're going to choose from this number, you mean?
What's that?
We have to choose from this number, from the phone number?
Right, so you pick from one of those numbers should give you, Okay? One of those numbers should be the correct molecular weight for calcium sulfate. Okay? So calcium in the periodic table is about 40 grams per mole. Sulfur in the periodic table is 32 grams per mole. And there are 4 oxygens. So it's 4 times the 16 plus 32 plus 40. Okay, so you got to sum up all the weights of things on the periodic table. Okay. Yeah. And so the answer is 136. Okay. And so you should be able to calculate that kind of question. Okay. And again, this is a perfectly good question for the first test. What is the molecular weight for calcium sulfate? Right. 136. Okay. So now we're going to get into more complicated problems of using molecular weight, but that's not to say that molecular weight is not a focus of our first test, that this may be a legitimately first question for our first test. Okay. All right. So the next part then is using the molecular weight. Okay. So we don't want to just be able to calculate the molecular. Being able to calculate the molecular weight is relatively easy. Okay, we have the periodic table. If we have the molecule, we should be able to multiply and add in order to get the molecular weight. But we want to do more than that. Okay. When we look at the law of conservation of mass, when we do a chemical reaction, when I am burning propane to make carbon dioxide and water, okay, the reaction that we're going to talk about, the conservation of mass, is conserving moles. Okay, so if I have methane, okay, which is a single carbon, okay, methane and oxygen makes CO2 and water. So the one mole of carbon in a methane will give me 1 mole of carbon in carbon dioxide that gets produced. So it is moles that are the unit that we're interested in for chemical reactions. Okay, so we have to be able to calculate how many moles are there of various components in a chemical reaction. Okay. But my scale in the lab doesn't measure moles. Okay. My scale in the lab measures grams. So we have to have a way to calculate between grams and moles, which we do now with the molecular weight. Okay. Like we used in the first chapter, density was a conversion factor between mass and volume. Okay. Molecular weight, molar mass, atomic weight, whichever term you want to call it, okay, is now a conversion factor between mass and moles. Okay. So here's an example of how this works. Okay. How many moles are there in 50 grams of lead-4 oxide? Okay. Now in this case, I've given you the formula for the lead oxide. Right? So you would look on the periodic table and you would find lead is 207 and oxygen is 16. And then you would put those together and get the total molecular weight for the lead oxide as 239. Okay, again, there's 2 oxygens, right? So there's 2 of those, and then the lead. Okay. So now I have 50 grams of lead oxide and the molecular weight for the lead oxide. Just like in the unit conversion we talked about before, we want to start with the simplest term. Okay, mass is a simpler term than grams and moles. Okay, this is 2 units. Grams per mole is 2 units versus grams is 1 unit. So 1 unit is simpler than 2 units. So we want to start with the mass. Okay, we're going to put our mass opposite. Okay, that's where our step is going to be. Okay, again, that's what's telling us where we're going to go. So the mass is grams per mole, just like the density, grams per milliliter. Okay, we divided by our density before. Now we're dividing by the molecular weight. If I take my mass divided by my molecular weight, I get the number of moles of lead for oxide.
I have a question.
Yes.
Why does it have 230 points? Is that just a mistake or?
Is it?
Maybe I'm just confused.
Let me check here.
230.2 and then the molecular weight, and the question is 239.2.
Oh, yes. In the
I just want to make sure it's a mistake.
I see where you're getting at.
Okay.
Yes, typo in that. So then the question is, did I then do the calculation right? Yes, so I did the calculation with the right number. I just didn't write the right number in there. Yes, molecular weight is the 230. Okay. I would like to say that I put these things in there to make sure everybody's still on their toes and, you know, that everybody's scratching their head about where numbers come from on the slide, but it's more my attention to detail than me trying to catch anybody. Okay. So this slide here is a slide that you're going to see where I begin to talk about a process for how do we solve problems that we can apply to a variety of chemical problems. Okay, so in the first chapter, we talked about how do we calculate volume and mass? How do we go from volume to mass? Or how do we convert between mass and volume? And the answer was we need to have the density. The density allows us to convert between mass and volume of different substances. Now we're adding this other step. If I want to calculate between mass and moles, I need the molecular weight. Okay, you'll have to get used to some of the slides interchanging some of the words. Again, I don't make all of these slides. My tendency to call things molecular weight is overridden by some of the slides that use molar mass as a term. And then if I wanted to convert from moles of something to how many particles there are. So if the question was asking how many molecules are there of the lead oxide, the way I would convert to that is to use the definition of Avogadro's number. Okay, in every 1 mole, there are 6.02 times 10 to the 23rd particles of whichever quality we're talking about. Okay, there are 6.02 times 10 to the 23rd molecules. You may also see it as atoms or electrons. Okay, but this begins to build us a kind of process flow chart that helps us to understand what steps should I be taking when I'm doing a problem. Where am I starting from? What's my first step? How do I solve this problem that's given me volume and wants to know how many molecules are there? Okay. Especially if it doesn't give you a lot of information. Okay. So the process flowchart helps us to understand what information do we need, how do I start my practice, how do I start my problem, and then, you know, basically how many steps should I, what is my next step in my calculation that I should take. Okay, and so you'll see me use this all the time because this kind of same process flowchart, we can apply it to any number of chemical reactions. Okay, So think of it like, again, if you learn a process for anything and other things fall within that same process, then you can convert one thing to another, right? So if you're used to, I don't know, like fishing in a lake, it's, you're roughly applying the same methodology to fishing in the ocean, right? You have hooks, you have bait, you apply the same kind of methodology, and you end up with fish in the end, right? So how we go about doing things, we can apply to various kinds of scenarios. Okay. So this would be a difficult problem here, okay? How many molecules of water are there in 100 milliliters of water? The density of water at room temperature is 0.987, okay? So let's go back to our slide. They want to know how many molecules of water, okay? That's a particle amount. And we're told the volume, okay? 100 milliliters, okay? So now I have to get from the top part all the way down to the bottom part. So this means that as you see the answer here, it's going to go from, you're going to see the first step is to use the density. That's going to be the first number that you see in there, okay? Or the first number after the volume, okay? The volume is where I'm going to start, okay? They already gave us the density value. They gave us the density value, but that's not where we're going to start. We're going to start from the volume. We're going to use the density first. Then you're going to see a molecular weight, and then you're going to see Avogadro's number. Okay. So this helps us to understand what other kinds of things do I need before I can start this. Okay. We already have the density, the first part, but we don't have the molecular weight. We need to go ahead and calculate that. Okay. Avogadro's number is a constant, so generally this is given. And so we would expect that our answer should go through 3 steps to get to the end. And here we are, okay? Here is the solution, okay? Did I say it? It's 100 milliliters. No. All right, so I changed the problem changed from 100 to 1,000 milliliters in my 2 slides. So this one's not a typo. The first, it's supposed to be the same problem, but I changed it to 1,000 milliliters instead of 100 when doing this. So 1,000 milliliters. Again, the process works whether it was 100 milliliters or 1,000 milliliters. Okay, so that's why a process works. That's how a process works. Is it doesn't matter what the problem is. Okay, we could talk about gallons of water. We could talk about liters of water, microliters of water. It doesn't matter. The first start is going to be the volume. Okay, so my first calculation here is the density. If I stop right here, the volume goes away and leaves me with the mass of the water. Okay, the next step was the molecular weight. Right, so I'm dividing by the molecular weight. If I stop right here, it's stop at step 2. Okay, if I stop at step 2, I stop at the number of moles. And the last step here is simply the definition of Avogadro's number, that in 1 mole, there are 6.02 times 10 to the 23rd molecules. So we multiply all the numbers on the top, divide all the numbers on the bottom, and we get 3.3 times 10 to the 25, 10 to the 25th molecules of water in a liter of water. Okay, step 1, step 2, step 3. Density, molecular weight, Avogadro's number. Density, molecular weight, Avogadro's number. Okay. Most problems can functionally be done in about 3 steps. Okay, and so you'll see we talk about steps 1, 2, and 3 a lot. Most of our practice problems, even when we convert from, even when we're doing more complex chemical reactions, we can generally hit this in mostly 3 steps. Okay. Questions on this so far? Is that I'll probably have another video of practice problems on doing this particular kind of thing. So if I don't have one already, I think I have a mass to mole video for practice problems. But it can never hurt to have one more probably. Okay, so the question of whether or not we can go from volumes to moles using 22.4 is used from gases. Okay, so that's actually a gas function. So that is called the molar volume that applies to gases only. Okay, so the 22.4 is a conversion of volume to moles, which we'll talk about other conversions of volume to moles because there's also molarity. Right? So in one of the other chapters, we'll talk about molarity, which is in mole per liter, which allows us to convert from liquid volumes, so we don't need the density, right? So there is a way to get around using the density. We don't always have the density of solutions, but we have the concentration, right? So like our lab for physical properties, there we looked at percentages, but generally we don't work with percentages for concentration for solutions. So we generally have molar values for solutions, so we can go from volume directly to moles in a solution value. Right? This is just a longer route, and then when we get to the gas chapter, there will be another step. So again, this flow chart is going to be a process. Okay, it is going to be a process that we build on. Okay. Every chapter where we do additional work, we're going to continue to build on this process until it is a bigger chart. Okay, you're going to see a lot of other steps and bubbles and things put all over the place. And so you can look at, and once you have an understanding of how to use the process chart, you can go from any kind of chemical reaction and solve chemical, like stoichiometry problems, and calculate masses or volumes or amounts of output from chemical reactions, and you should be able to do that to just about anything. Okay, so the process flowchart will expand as we look at different areas. Okay, all right, so that is it for this chapter. It's a relatively short chapter. Okay, so what we'll do is we'll end here, and we'll take a short break, and then we'll come back and we'll start looking at nomenclature.